So some reminder. So let me recall that the algebra of symmetric functions is defined as a projective limit in the category of graded algebras of symmetric polynomials in n variables, and all over Z. It's important. And next, the algebra of symmetric polynomials can be identified with the ring over the elementary symmetric polynomials. And this leads to the presentation of the algebra of symmetric functions as the algebra of polynomials in infinitely many variables identified with elementary symmetric functions. And let me also recall the generating series for the H and E symmetric functions. So this is the generating series with the understanding that the H0 is 1, and likewise the generating series for the elementary symmetric functions with the same assumption. And there are formulas, explicit expressions in terms of the variables, of the initial variables, the x's. And similar formula. And which implies the relation for these two formal series. This one. And this leads to a collection of identities of such a kind. And this one, and this leads in turn that the algebra of symmetric functions can be also identified as the algebra of a Z over the H, over the H functions. So this is also important, this identity and this identity. And we also have a basis. The Schur symmetric functions. And here, lambda is an arbitrary Young diagram. So we have, one can write as an abelian group. It can be identified in this direct sum. And from this identity, from this fact, This implies that any Schur polynomials, any Schur symmetric functions can be written as a polynomial in with generators. And so the question is how to write this polynomial explicitly. And this is a very important result, which is called Jacobi-Trudi identity formula, one of the fundamental facts of a symmetric function theory. It says the following. So for any Young diagram, the following formula holds true. Is the determinant this matrix. So the question is how to understand rigorously this expression. First of all, we see this matrix is infinite in principle. In principle, it is infinite. But first of all, we have to agree that Hn is equal to 0 if n is negative. We give no sense for the h functions with negative index. And next, we also, let me recall that h0 is equal to 1. So this matrix is of the form something, and so it is almost unitriangular. And this means that this determinant can be understood as determinant of the n by n corner, provided that n is large enough. Then this determinant is finite determinant, does not depend of the choice of n, and actually it's sufficient to assume that n is greater or equal to L of lambda. L of lambda, I recall, is the number of 0 rows. So we may assume we can truncate this matrix at the level n, which is large enough, say equal to the length of. So this is just a comment to the claim, to this claim. How to understand this? So how to prove? How to prove this proof? Some general principle is because the symmetric algebra is the projective limit. If you want to prove something, some identity, some formula, it's enough to prove it in n variables. So just take its image in this quotient algebra and verify it with n variables. If n is arbitrary, then we can conclude that this formula holds true in the whole algebra of symmetry. So let's apply this general principle, and we will prove this identity for polynomials in n variables, and we will assume that the length of lambda does not exceed n. So we can deal with polynomials in n variables. Right? So there are several possible approaches to the proof, and I like the mostly the approach through the Cauchy identity. So let me recall the Cauchy identity. In n variables, infinitely many variables, it is as follows. The sum of all Young diagrams with at most capital N rows, and we have n variables, y's, and the result is the product, the double product. Very simple expression. So my goal is to derive from this Cauchy identity the idea, the Jacobi-Trudi form. How to do this? Again, there is a very important principle, some general principle, which says the following. So assume we have some formal power series which is symmetric. It's convenient to write it in variables n, some power series. It's not necessarily one can write any field R. It's not important. Formal power series is symmetric. Symmetric with respect to permutations of variables. And because the Schur polynomials form a topological basis in this ring, one can expand this formal power series in the Schur polynomials. So one can write it as follows: some coefficients and the Schur symmetric polynomials. And the sum over all lambdas is above. So the question is how to extract, compute the coefficients. And the idea is very simple. Let me write it. The idea is as follows. Let me write first, and then I will explain what this means. It's written here. First of all, so this is a monomial, it's clear. This is the van der Monde. This is our symmetric power series. So this notation just means extract from this formal power series the coefficient of this monomial. This is some notation in combinatorics of such a type, which means that we want to extract the coefficient of something in the expansion of some expression. Okay? So this is why this claim holds true. this one. This is very simple. Just look at this. Right. This just means that we have multiply the van der Waals and we get the sum and the alternance. This determines sum. So just look at this determinant, this alternant. So just pick the leading term, which is this one in lexicographic order. And we see that this coefficients is just the coefficients corresponding to this monoid. Is it clear, or maybe some questions? So please ask. So this is very simple, but very important device. So just apply it.
Ну, у нас там справа стоят детерминант от матрицы с иксами. У нас там разве не y должны быть?
Да. Это верно. Это верно. Большое спасибо. Это, конечно, я привык писать иксы. Мне удобно в этой ситуации написать игреки. Сейчас увидите, почему. Большое спасибо, что вы меня поправили. Конечно. Тут никаких иксов на этом уровне нет. Ну, хорошо. Well, so just apply this principle to this. Okay? To this form. So we take as f, we take the right hand side. This is our f. And just work over the ring of symmetric polynomials. So we just regard these quantities as coefficients. So what I want to say, part this formula is an identity of formal power series in the y variables over the base ring, which is in our situation this one. So the idea is to treat the symmetric polynomials in the axis as scalars, as elements of a base ring, this one. And now we can apply this general principle. So it gives us next. So we have f is this one. The x's are coefficients, something from the scalars. But this is nothing else. This is also an important remark. Okay. And from this we can write the desired coefficients. These polynomials are simply coefficients in our picture. So we have extract these coefficients From what? From this product. Okay. Well, but what this means? This means that this expression this is the determinant okay. So let us rewrite it slightly. This just expand. So this is the sum of permutations, the symmetric group of what? The sign of a permutation and the sum just expand the H functions, the H series. One can write as follows. And next we have this part. This part comes from the expansion of this quantity, and now we expand the determinant okay. And we have to extract we have to extract from this expression the coefficients of the monomial and to do this, how to do this? Just look at what happens. To do this, we just to specify to do this, we have to specify these numbers so that they satisfy the system of relations. What system? Namely, just we equate the coefficients, and next, in this way, we get a system of relations. Is equal and this just And this just means, that and if we understand you, okay, so this just means, and this means in turn that the h's, just look at the h's which come here. This leads to the fact that the coefficients we need is the sum of the permutations, the sign of a permutation, the product because this comes from this product. Once we specified the m, we just get this expression. But this is exactly what we want. This determinant. And with the understanding that in the expansion of this determinant, because some monomial which corresponds to some sigma should be equal to 0 if some of at least one of these quantities is strictly negative. And this just corresponds to our agreement that these quantities should be equal to 0. So we get the result. The formula that we... Some questions maybe? Is it clear? So this is just a formal manipulation. But let me emphasize that the key, the proof is the Cauchy identity. And some immediate consequences. So some consequences. First of all, we also get, so that maybe right. This is the transposition map, involutive transposition map of a set of Young diagrams, which we regard Young diagram as this picture. We just take the reflection with respect to the main diagonal, the symmetry. This is called the transposition of Young diagrams. And we have the immediate consequence, corollary. Corollary is as follows. So we have a similar expression in terms of the elementary symmetric functions. Take the transposed Young diagram. This is because we independently proved at a seminar that this determinant is equal to this determinant. So we get this important result, which expresses the Schur functions in terms of elementary symmetric functions. What next? Let me recall that it is deduced from formally from the identity. And some combinatorial fact, which is called Frobenius. Next, the involution map. Involution. Involution map, because we know that the symmetric function, the algebra of symmetric functions can be represented as polynomials in the H's, as well as the polynomials over the E functions. We can define omega an automorphism, which sends the H function to the E function. And from this identity, one can deduce that omega is involutive, meaning that the square of omega is equal to the identity map. This is an easy exercise. But note also that it is also agrees with the fact we see that this follows from Jacobi-Trudi and Dewey-Jacobi-Trudi.
Можно спросить,
Да, пожалуйста.
а почему омега гомоморфизм колец?
У нас одна система образующая переводится в другую систему образующую. Это отображение продолжается до автоморфизма колец полиномов. Понятно ли?
Спасибо.
То есть у нас есть две системы свободных образующих. Между ними нет никаких соотношений, ну, в смысле коммутативной алгебры. Свободные коммутативные алгебры от одного набора, от другого набора. Можем произвольным образом взять биекции одного набора на другой набор. Ну, автоматически продолжается морфизма алгебры.
А если мы знаем, как вот омега отображает только из H в E, а почему мы, например, можем сказать, что мы знаем, как отображается произведение H, куда оно отображается с помощью омеги?
Произведение отображается в произведении. Суммы отображаются в суммы.
Но это так должно быть по определению гомоморфизма, а вот почему оно так продолжается?
Попозже. Извините, давайте мы это подробно обсудим. Давайте. So from this identity, it's also obvious that omega is involutive. This is immediately see also from this. So what is important? I would like to emphasize. It's trivial, but it's important. So omega is defined on the level of symmetric functions, but not in the algebra of symmetric functions in n variables. In n variables, in this truncated version, omega is not defined. It appears only on the level of symmetric functions. This is a manifestation of the fact that things become simpler on the level of infinitely many variables. It is on the level of symmetric functions and not polynomials. So sometimes it's convenient to work with finitely many variables, but sometimes it's much better to use infinitely many variables, that is the algebra of symmetric functions. This gives us more freedom. This is trivial, but important. So what next? So far, I emphasized that the base ring is the algebra, is the ring Z of integers. But sometimes it's more convenient to work over some field. So we can also consider the algebra, say, over the field of real numbers, which means we take this one and recall that in this, but not here, so not over Z, we have a, oh, I'm sorry, not exactly, so forgot this. Okay. So introduce, let me recall the definition of a power sum symmetric functions. So is the sum of coordinates and again a very simple but important remark. It is convenient to assume that these objects are equal to 1, but there is no sense is given to this. This object does not exist. So took this some decision. Okay? Never, or almost never, consider this is forbidden. So the next remark or some proposition is false. So extend our omega to this algebra of the real fields. And the claim is, so this claim is not necessarily to assume that we are working over R, but it will become important for the proof. So the claim is this one. So this is a claim. So what is the proof? So this is because I want to use this generating series. I want to divide by n. And because of this, I need the field and not the ring of integers. So we know that this is the logarithm of h of t. Now, in order to prove this, let's prove this in terms of generating series. So just apply coefficient wise. Just compute what happens. So this is this is coefficient wise. Next, we recall what is H. So this is no, maybe it's better to write no. We know that this is equal to because we know that omega transforms H to E. This is equal to product and this is equal to the sum of a sum and this is equal to this is finitely this one. Comparing the coefficients, we see that we get this property. This. So the idea is very simple. Just use this relation together with the fact that H is transformed to this one. Well, what next? Next subject. Is it clear, or maybe some questions about this manipulation?
А в сумме идет суммирование по n или по i, или вот что имеется в виду, там n стоит
Да,
n.
вы правы, да, это вы правы здесь. Спасибо, да. Это что-то я запутался в трехсотых. Да. Двойная сумма. Здесь двойная сумма. Здесь двойная сумма. Я просто разлагаю логарифм в ряд. На этом деле я запутался. Что-то у меня вдруг переклинило мозги. Прошу прощения. Спасибо. So The next topic is the scalar product. And here I want indeed to work over the real numbers. So let me recall that this algebra is graded. And the components, homogeneous components, are finite dimensional. We defined scalar product. In this infinite dimensional vector space by assuming that, by proclaiming that the basis of Schur functions is orthonormal. That is, scalar product of two symmetric functions is the chronicle delta. So in particular, these homogeneous components are orthogonal to each other and is not equal to M. So this decomposition is an orthogonal decomposition. So the scalar product in this sense is consistent with the grading. Let me recall again the Cauchy identity. With infinitely many variables, it can be written as follows. X, capital X, capital Y is equal to the double product here I assume that X, capital X, is this collection of variables. Y, likewise, is the collection, infinite collection of variables. And all this is in, well, belongs to a algebra of the real numbers of formal power series in double infinitely many. So this makes sense as an identity. This makes sense as an identity with this algebra. Okay? So why it holds true? Because it holds true for finitely many variables. And we have the following position. So assume we have two homogeneous basis in our algebra with infinite dimensional space, but graded with finite dimensional components. And homogeneous, which means that this basis is compatible with the grading. So we get a basis in each homogeneous component. So we have assume that we have two bases, and they are also indexed by Young diagrams with the same assumption that belongs to components equal to the number of boxes. Likewise, for another basis, just as for Chopin. And the claim is as follows. So we assume the claim. So maybe let's say that this basis, two bases are bi-orthogonal if we have these relations. The scalar product is the Kronecker delta. So this means bi-orthogonality. So the claim, now the claim two bases are bi-orthogonal if and only if we have this identity just as for sure functions. Maybe we write according to my notation. So these two properties, one is the property of bi-orthogonality, and another is this relation which is similar to Cauchy identity. These are the same. So how to prove this? Prove. So we, the right hand, this can be restated. This is the same as to say that bi-orthogonality is equivalent to the equality so this is trivial. So we can prove this equivalence. And how to do this? We can assume, may assume that we take the sum over the set of Young diagrams with n boxes, which corresponds to the picture which happens in the homogeneous component of index n, because all is compatible, consistent with the gradient. So we can assume that the sum here is not over the whole set of Young diagrams, but only over the set of Young diagrams with n boxes. So then this quality is the same as the following one. So all this happens, inequality, in what? The tensor product of two copies of a finite dimensional vector space. This is the identity. So I claim that this with the sum over this finite set is the same as this. This is trivial, just by the definition of a tensor product, actually. So, and now, actually, we can forget about the symmetric functions, all that. We only have some vector space, finite dimensional vector space, non-degenerate scalar product with vector space, and orthonormal basis, some orthonormal basis in some vector space, some abstract vector space, and two bases, and the claim is that this equality, this vector space, is the same as by orthogonality of this and this with respect to the scalar product. And this is easy to see by, I don't want to change the notation, and just I will still work with Schur functions and so on. So just take transition matrices. From our basis, initial basis, this one, to this one, onto this one. So we can just write that some likewise. So these are two matrices. transition matrices F and G. And by orthogonality, and we use the fact that this is an orthonormal basis. And then orthogonality just means this relation transposed equal 1. Okay? And this equality means it's exactly the same. You want to prove this using the expansion. We just get the same relation. So we get this equivalence. So this is pure linear algebra. Nothing else. Some questions, maybe? So please ask if there are some questions.
Да, можно, пожалуйста, еще раз поподробнее, почему мы в самом начале доказательства сказали, что мы можем рассматривать суммы только по конечным диаграммам?
Почему мы хотим это сначала? Это понятно. Потому что мы хотим работать, все сделать конечно.
Ну да, а вот почему мы можем так сделать?
Почему мы можем? Потому что у нас наш базис по предположению согласован с градуировкой. То есть мы считаем, что фактически у нас в каждой однородной компоненте выбран базис. И весь наш базис, он собран из этих кусочков. У нас есть набор конечномерных подпространств. В каждом конечномерном подпространстве есть свой базис, занумерованный лямбдами с n клеткой. И поэтому все это хозяйство рассыпается. Нам нет необходимости следить за всем этим бесконечным хозяйством. Мы можем сфокусироваться на любой однородной компоненте и смотреть, что внутри нее происходит.
Да, понял.
Более,
Спасибо.
что они все попарно ортогональны. То есть мы редуцируется у нас к этому конечномерным компонентам.
Спасибо.
Еще, может быть, какие-нибудь вопросы, пожалуйста, тогда спрашивайте. И, может быть, еще последнее, что мне нужно рассказать. Все это нужно мне будет потом мы вернемся уже, наверное, уже в следующую лекцию, уже мы вернемся к представлению. Поэтому все это хозяйство не просто так, хотя оно, конечно, очень интересно и само по себе, но это, так сказать, подготовка к выводу формулы Фробениуса для характеров симметрических. So, application to P functions, power sum functions. So let me set P under as the product. And here just maybe it's better to write if I assume that, of course, I don't want to say what is R is the length. So this is the definition. So this is a symmetric function. This is an object in. And this is a basis. Is the basis in what? In this algebra, not in the algebra, not in the initial algebra of the Z. These functions belong to the Z algebra, but to get a basis, we need to use the extension, the extended algebra. It's convenient to use a different notation for Young diagrams. So maybe in this context, it's convenient to read Young diagram as partitions, not as pictures, not as picture like this, but partitions. We read them as sequences like this one and use the so-called multiplicative notation. So right. It just means that A is the number, maybe the number parts equal to M. So this is a different notation. Or one can say that our Young diagrams has this number of one box diagram rows. So we have some picture like this. So this is multiplicative notation. And some notation I need also is this one. So if K, the multiplicity, this multiplicity is equal to 0, then this quantity is equal to 1. So this infinite product is actually finite product. One can write here this. This is this. So what I want now? So we claim is this. These functions. This is an orthogonal basis. Orthogonal basis in the extended algebra, but not orthogonal. And namely, we have this formula for the scalar product. So this factor means that the basis is orthogonal, but this quantity means that it is not orthogonal. The norm is equal to the square root of this expression. Okay? So first of all, why? So the proof. So why is the basis without the claim of orthogonality? So this because of this claim that not because it is follows, it's better to say, can be derived from this relation. So one can prove that the p functions, the power sums, can be expressed in terms of h functions and vice versa, and these transformations are triangular in a certain sense, and this means that the p functions also can be taken as algebraically independent generator of our algebra, but only over the base field R, not over Z. But now I want to prove the orthogonality. How to do this? And just use this claim. So to do this, prove orthogonality. Or actually by orthogonality, which means that the basis is y orthogonal to this one times these coefficients. To prove the orthogonality, we need to prove the following. We have proved the relation is how to do this. It's convenient to take a logarithm. So take log of the right hand side. This log.
А почему это достаточно для доказательства ортогональности доказать это тождество?
Потому что это то же самое, что я говорил раньше. Мы берем это в качестве f от лямбда, поэтому у нас будет g от лямбда. Тогда то, что мы хотим, это мы хотим доказать, что вот эти два базиса биортогональны. Это утверждение, которое у нас есть.
Спасибо.
Значит, теперь compute this. What is this? This is the sum over I and J, double sum over M, this one, and this can be written as this one. This one. And so we get that the right hand side is equal to the exponent, the sum what is this? The exponent of a sum. So this is something like this one. Let me write just to make it more clear. And this is the sum.
Там еще ведь под знаком логарифма получается произведение должно быть, когда мы только начали с правой частью работать.
Где произведение?
Ну вот когда вы пишете take log right hand side,
Да,
логарифм, и тут ведь под логарифмом должно быть произведение вот этих дробей.
да, спасибо большое. Да, конечно, спасибо. Спасибо. Спасибо большое, конечно. Это я призывал. Так. Что я хочу? What I want to say. This sum of n. This is the binomial, multinomial coefficients. And this. And so on. And this is exactly what we want. So this denominator just comes from these factors and from these factorials, and these factorials is cancelled with this factorial. So we get, this is simple, we get this. Well, so I have to stop, switch off recording.